So in this video, we're going to talk about how a UV visible spectrophotometer records absorbance measurements. So in the UV visible spectrophotometer, there is a lamp which releases a light, I sub naught, which hits the sample. Now a certain percentage of this light, represented by I with no subscripts, then hits the detector. The UV visible spectrophotometer uses the relationship between the light that hits the sample and the light that actually passes through the sample and then hits the detector to record an absorbance. This relationship is governed by Beer's law. So the absorbance is equal to the negative log, that's a base 10 log, of the transmittance, where the transmittance is equal to the ratio of the light that hits the detector, I, over the initial light, or I sub naught. That's a negative there. And we can do a little bit of algebra to rearrange this equation to give us a positive log of A is equal to the log of I naught, or the light that hits the sample, intensity of light that hits the sample, divided by the I, or the intensity of the light that hits the detector. Now, if we find ourselves in a situation where all of the light that hits the sample goes through and then hits the detector, the ratio of I naught to I would be 1. And so for a situation where all the light passes through the sample, the negative log of 1 is 0, so we would see an absorbance value of 0. If we found ourselves in a situation where none of the light was transmitted through the sample, and our ratio of I naught, or I to I naught, would effectively be 0, we would get a negative log of 0, which mathematically would reduce to an absorbance of infinity. Now, neither of these situations where 100% of the light hits the detector or none of the light hits the detector are particularly useful. And so depending on who you talk to, there are different frames of reference for what absorbance values are acceptable to measure based on how much light hits the detector. So how much of an absorbance would lead to either too much light being absorbed and overwhelming the detector, or not enough light hitting the detector. So generally speaking, we don't want to see an absorbance value that's greater than 2. And that's because if we go ahead and we do the algebra, we cancel out the negative log on both sides, we get that the ratio of I to I naught is 0.01, or only 1% of the light passes through and reaches the detector. And so most people would agree, that an absorbance value greater than 2 is useless. And so many spectrophotometers won't even record an absorbance value much higher than 2. Now, in my experience, I have always been taught that a good frame of reference for making measurements is to keep your absorbance values between 0.1 and 0.9 absorbance units. That doesn't mean, and by the way, absorbance units, I actually shouldn't put an A there because absorbance has no units. Now, different scientists may have different ranges and within which they operate, and you may see people recording absorbance values of greater than 0.9. For instance, if we have an absorbance value of 1, if we were to propagate the math here, we would find that at an absorbance value of 1, 10% of the light hits through the detector. So you may or may not, an analytical chemist would have a better explanation for what an acceptable limit would be, but for the limits that I have always used in my research, so between 0.1 and 0.9, here are the percentages of light that would hit the detector based on these absorbances. So for a value of 0.1, we get a ratio of I to I naught of 0.79, or approximately 79%. For an absorbance value for an upper limit of 0.9, we get a ratio of I to I naught of approximately 0.125, or 12.5%. So for the limits that I use as a guideline in my research, I see an upper limit, or for a lower limit of 79% of the light hitting the detector at a 0.1 absorbance, and that an absorbance of 0.9, I would see 12.5%. And again, depending on the technique, the application, the scientist, the field, you may see slightly different recommendations for what is acceptable, but know that the rationale for how we pick these boundaries is based on how much light hits the detector or how much light isn't hitting the detector. And you'll hear more. In fact, you'll hear all about this in subsequent courses, especially in analytical chemistry.